In our last session, we have completed SQL. So now let's see the data warehousing concepts. Data warehousing and data modeling. One second, I'm adjusting my screen. Okay, so data modeling and data warehousing. These are sometimes referred as similar concepts or referred as different concepts, but the core concept is the same. Okay, first let's see the data modeling. Data modeling means, let's say, when you are working for any business, okay, uh, let's say for the e-commerce Amazon website, if you are working for that Amazon client, you need to store their data in an organized manner, and which helps us to query the data efficiently and also build the reports efficiently. Okay, how is that possible? So that is possible through data modeling. Data modeling means, so in our earlier examples, while working with the employee or the department table, if we have maintained employee ID in the department table, the data has become redundant or there is a violation because department ID is the primary key. We are not able to maintain multiple employees in the department table. So that is not a good modeling idea, right? So later what we have did, we have switched the department ID into the employee table. For each department, there we can have any number of employees. Employee ID being the primary key. So we can have any number of employees to that department. So that is the way we have changed our model so that we are able to fit our requirements. So all these kind of things. So in which table, what kind of data has to be presented, all of that decisions has to be taken during the data modeling. Okay. It is like a blueprint. It's like a blueprint of the data, how it can be stored, managed, and queried efficiently. So data modeling is, it's a structuring of these concepts are very, very, very important. It's about structuring of data to store, manage, and query efficiently. Okay, we have to consider all the aspects, how it has to be stored, how it is to be managed, and how efficiently we can query efficiently. Okay, so here we will know like organization of the data. Organization means arrangement of the data. Organization or arrangement of the data, like which table contains what kind of data. Arrangement of data in tables, their relationships. Relationships are like, if you take that employee or the department table, what is the relationship between them? We are joining on the department ID. That department ID is the relation. Relations are also of multiple types, one to one to many, or many to one, or many to many. Okay, so the relation, it will define the relationships between them, and also what are the relation keys, what are the primary keys, what are the foreign keys, etc. All of this is decided in the data modeling. Okay, it's like a blueprint of our data. Blueprint of our data. Okay, so this data modeling can be done in various layers. Okay, types of data models. These all seem to be theoretical, but when you are actually implementing the data or the tables, we have to use this all the concepts. Maybe this happens at the very early phases of the project. So let's say we don't have any project in place for the e-commerce website. Let's say we don't have anything in place. We are starting from the scratch. Then all these things comes into picture. Otherwise, you very rarely see these things being talked in the projects. but you have to understand what these are. Even if it is not in the beginning phase, later also you need to join the tables, you need to write the queries, you need to uh, define the relationships between them. All of this has to be done. So this is important. Types of data models, or we can say the how data modeling is done. It can be done in three levels. Okay, the first is conceptual data model, which means here we will talk conceptually about the business. Let us say we are talking about the Amazon website. What is expected what is expected in the Amazon website? What basically happens over there? There will be products, or there will be manufacturers or the sellers who will be selling the products. Okay, and there will be customers who will be purchasing those products. And Amazon is the bridge between the sellers and the customers, right? So what happens over there? The major business is uh, selling or purchasing. If you talk from the seller's perspective, it is selling the products, or if you talk from the customer's perspective, it will be purchasing the products. So whatever it is, what happens here is we will have customers, and we will have products, and we will have orders. Okay. So on a business level, we will be understanding the data. So let's say understand the data on a business level. Okay, what business happens and how what we need to derive out of that. Okay, no technical details. So here not we are not talking about any table or any IDs or any keys. We are not nothing. We are not talking anything technically. We are talking all about the business level. Like what kind of business happens and what do you need. Okay. So they will tell that this all comes from the business. They have to say this. In our business, this is what is going to happen. We have a website which will list down the products, and there will be customers who will be purchasing those orders. They will give you that clarity. Okay, so we will understand. Okay, on a high level, these are the type of data sets we are expected. Okay, now comes the logical data model. Now you have understood the business. Now we have to convert that into logical data model. It is like in extension to a conceptual model. Extension to conceptual data model. Here we will go into more details. Okay, more details to the conceptual data model. Here it is more detailed, and here we define attributes. Attribute means columns. Attributes generally referred to as attributes or columns. So here we have to define which table should contain what columns. Maybe in the customers table, we are expecting customer ID, customer name, address, location, all of that we are expecting in the customer table. Similarly, for products and orders, what are the expected things, columns? Okay, and what are the primary keys? Not only primary keys, any keys basically. Primary keys, the relationships. What is the relationships? So all of these are designed or decided in the logical data model. Okay. So all of these things are decided in the logical data model. And now finally comes the physical data model. Here we are like documenting. Let's assume this is the documentation part. And now finally we have the physical data model where we really implement it on the database. Physical data model. Actual implementation on the database. Okay. So it might be a SQL server, Microsoft SQL server, which we have worked so far, or it might be a Snowflake cloud data warehouse, or it can be anything. Our database can be anything. It will be decided by our business, or we have to propose which database has to use for this model and how and why. We have to tell the advantages and disadvantages of any server you are proposing. Okay. Snowflake, because of its features or ease of use or flexibility with the cloud platform, we are using this Snowflake. Okay, so there might be organizations where they might be using the other servers also because of the sensitivity of the data, maybe for banking applications and all. They don't want to expose the data to the outside, so they might be using the SQL servers, which are hosted on their organization within the organization premises. Okay, so it all depends. Don't worry about this servers where it is or how it will be hosted. Don't worry about that. So now we are talking about the data modeling. In the physical data model, we will be actually implementing it in the database. So we know the business now. We also know what fields are there, what are the keys available, and what are the relationships between them. Okay. So here we include table names. We have to decide what tables we are going to have and what are the names of that and data types of the columns. Y- But I hope that by this time you are able to understand what is a table name, what is a data type, all of that, right? So indexes, are we going to have any indexes on the tables or do we have any constraints on the table? All of these terminologies we have discussed. Okay, so we will actually implement it on the database. This is what happens in the physical data model. So whenever you are building a new data model, it has to go through all these phases in an order. Okay, so let's write down. When building a new data model, it has to go through all these phases in an order. Definitely order is required, otherwise it's not possible. Let's say you try to do physical data model without knowing the business. How is it possible? Right? It's not possible. So you try to do the logical data model without understanding the business. That is not possible. Okay. Or else you directly go first understand the business and directly implement it on the database. That is also not possible. First, you have to analyze that data, define what columns are expected, what keys are expected, and what relationships are expected. All of that you have to decide, and then only you can really implement it on the database. Okay. So this is about the modeling. So maybe in the interviews they'll ask us what is data modeling, what are the different phases involved, and what is the order of this. Order of data modeling. So first is conceptual, logical, and finally the physical. So this is the order in which we do the data modeling. Okay, right. So let's talk about the relationships between the tables. Relationships. So we have one to many, one second, one to one to many to one, and many to many. Okay, let's see with an example. One to one means, let's say we are talking about two tables. Okay, maybe here, let us take orders and the customers table. Okay, orders and customers and products also. I'm talking about our e-commerce website, orders, customers, and products. Okay. If you take a customer, each customer should have only one customer ID. Okay. So let's say each customer should have only one customer ID. This is within the table itself. Okay. This is within each table we are talking about. Customer ID and customer name may be available in the same table or might be available in the different tables also. Okay, each customer should have only one customer ID or each employee should have only one uh, empl employee ID or each department should have only one department ID. That is about the one-to-one relationship. Or if you take this table, each order should be placed only by one customer. Okay, so each order, when I say order, order ID will be generated. That order ID belongs to only one customer. There is no possibility that the same order ID belongs to different customers. That is not possible, right? Or one order ID belongs to only one person. So this is the interpretation of one-to-one relationships. So when we are saying these two tables are having one-to-one relationship, it means that each row in the table 1 corresponds to only one row in the table 2. Okay. So each order ID corresponds to only one customer in the customer table. Okay, let's write customer instead of person. Okay, each order ID, it corresponds to only one customer in the customers table. Okay, so that is the meaning. Here, if you say one to many, one customer can place many orders. Okay, so on the left, on one table, we have only one entry. One entry in the one table corresponds to multiple entries on the other table. So this is the meaning of one to many. So the example is one customer can place many orders. Here if you see, order ID should belong to only one customer. One order ID should belong to only one customer. But one customer might have multiple orders. That is possible, right? I'll be purchasing AC and I'll be purchasing fridge as well. I'll be purchasing TV as well. So for the same customer, there is a possibility of having multiple orders. So that is the meaning of one to many. One customer can place many orders. So now many to one. What I can think of is the same thing. I mean, one to many. This can be referred in the other way. So let's take many orders will be placed by a single customer. Will be placed by a single customer. Or the best example for many to one is uh, multiple products, many products can be purchased in a single order. Let's say in a single order, I will add everything to the cart, whatever I need. Okay, a fridge, a washing machine, a TV. I will add those three products to the cart and place an order, right? So multiple products can be placed in a single order. So that is also possible. Multiple products placed in a single order. Okay. Also, we have many to many. So on both the sides, we have multiple entries in the tables for a single entity. Let's think of it like what we can have for multiple in this case. Mm, Okay, multiple products and multiple orders. So let's say we have a products table containing some products, TV, AC, washing machine, fridge. Okay, these are the list of products. Now with some product IDs. So each product ID should be different. 3 and 4. Let's say Amazon is selling only these four products. Okay. So here we have orders. Order 1 containing the products like 1, 2, 3. Okay. So order 2 containing the products 3 and 4. So TV is purchased. If you refer one TV here, TV is purchased in multiple lines here. Okay. TV is purchased in the multiple lines. Or if you take one order here, this one order is having multiple entries here. One order belongs to multiple products here. This is called many to many relationship. It might seem little confusing, but please try to understand. Like many to many means multiple entries in table 1 belongs to multiple entries in the table 2. Okay. Here what we can say, multiple products being purchased in multiple orders. Okay, that is the meaning of many to many relationship. Let's see if we find a best example over the Google. Best examples for data model relations. Okay, let's see here. How entities interact with common examples including one-to-one user profile, one-to-one customer orders, many-to-many book authors. Okay, let's see here. They were given, I mean, they are not talking about a single business unit. They were talking in general, the best examples here. Okay, let's see. In one-to-one relationship, they have taken an employee and a badge, which means each employee has unique badge and that badge belongs to only one employee. Either you refer it the other way, ID and employee, or employee and the ID. Any way you refer, it is a one-to-one relationship. Badge means nothing but the ID card. Okay. Each employee should have only one badge, or one badge belongs to only one employee. So that's a one-to-one relationship. Now let's see one-to-many. Customers and orders. A single customer can place multiple orders. That is what we have discussed. But each order belongs to only one customer. Yes. One customer can place many orders. But if you refer it the other way, it should be like one order should belong to only one customer. Okay, this is one to many. And many to many. See here, a book can have multiple authors and an author can write multiple books. Uh, if you consider the books, don't consider the novels because they are like a single author for each book. But if you take some technical books, maybe your engineering or the graduation books or your uh, any textbooks, technical textbooks. So each textbook can have multiple authors. Let's say in our engineering, for the physics subject, we have multiple authors. I don't remember the names now, don't ask me. Okay, so there are multiple authors for each book. So our professors or the lecturers will suggest. So for physics, the book authored by somebody is more important than the book written by some other author, right? So the same physics textbook, the same contents is written by multiple authors. Okay. Or the same author, whoever has written the physics textbook, they might also have written the maths textbook. Okay, the same author has written multiple books, or each book has been written by multiple authors. That's the meaning of many to many relationship. Okay. Okay, here they have given the e-commerce as customers as one. What is this? Customers, orders, and products. I think N refers to many. So between the customers and orders, we have one to many relationship because one customer can place many orders, and between the orders and the products, we have many to one relationship. N refers many, one refers one. So many means multiple orders uh, can purchase the single product. TV can be placed in, let's say we are talking about the product TV. It will be there in multiple orders. Maybe I purchase the TV, you purchase the TV, and some other person also purchases the TV. So multiple orders purchasing the same product. That's what it is trying to say. So that is about the relationships. You can dig more into that. Okay, I'm just throwing some light on each of the concepts. Okay, so right now we will say I'll write another example also. Each book, not each, multiple authors for a book and An author can write multiple books. This is about the relationships. And now we have another concepts called OLTP and OLAP. OLTP and OLAP. This is basically how the data is generated. How the data is generated through transactions. How your how your e-commerce data is generating? We are doing some transactions. We are purchasing something. That the purchasing is a transaction. So OLTP systems are transactional processing systems. Online transactional processing. OLTP stands for online transactional processing, and OLAP stands for online analytical processing. So, being a data engineers, our job is OLAP. OLAP means we have to analyze the data on the already uh, transacted data. Let's say if you want to do analysis on the Amazon website, which product is selling more or who is our best customer, what we have to do? We have to take the history of the orders, history of the purchases, or history of transactions from the Amazon website. From that data, I have to do group by on the customer and the count of orders for that. Whoever is having the more orders, that person will be the best customer for us. Or if you take a product, how many number of products are purchased for that particular unit? Let's say TV. If out of these four products, TVs were purchased in thousands, and ACs in hundreds, and washing machine maybe hardly 10, and fridge also hardly 10. Okay, then which is the best product, best selling product? Then TV, right? So these kind of decisions, how we are able to do based on the historical data, based on the transactional data, we are doing that. So being a data engineer, our focus is on analytical processing. But in order to do analytical processing, there should be transaction already happened. Okay. So there are two types of systems. Maybe in the interviews they'll ask you what is OLTP and OLAP, or what are the types of systems available. Okay. So OLTP and OLAP. So this is real time. Okay. Real time, like the Amazon transactions on the Amazon or the banking transactions, they have to be reflected immediately. So let's say you have placed an order on the Amazon website, it has to be reflected immediately in their database. Then only they will process the orders, right? And similarly, in case of banking applications, if your salary is credited, that should immediately reflect in our salary account, and also in their records, in the bank's records, it should reflect this customer so much amount is credited, or if you have spent some amount, it should immediately say this customer has spent this much of amount, right? Those are all real time. So it's e-commerce transactions or banking transactions, whatever it is, or all the real time transactions comes into OLTP systems. So whatever comes into OLTP systems, if you want to do analysis or do make business decisions, that has to be transferred to OLAP systems to enable business insights like best customer or best selling product. We need historical transactional data. The OLTP is real-time data. OLAP is historical data. Okay. So OLTP systems should work efficiently for write heavy operations. Write heavy means as soon as the transactions happen, it has to be written into the table. It has to be immediately written to the table. So it has to be write efficient in case of OLAP. So there is no urgency for us to get the transaction immediately. Our intention is to do the analysis. See, On what things we do analysis? On the historical data. Maybe for the last month, last year, we cannot do analysis for the current day. That is very rarely we can do. Because if you do analysis on a day wise, it might not be accurate. Okay, that's why we generally don't do analysis on the current data. We do it in the past month or the past week or the past 15 days. Always on the past, not on the real time data. Okay, real time means immediate data, I mean to say. It's not about some fake data. It's not about the fake or the real data. This is like real time. When we are talking in the data engineering terms, real time data means within the fraction of seconds, as soon as the transaction happened, the data should be made available. That's the meaning of real time. So otherwise, it is considered as batch processing. Batch processing means the transaction happened yesterday. Maybe we are processing it today into our analytical systems, because analytical system doesn't have an urgency. So we all do it on the historical data, so there is no urgency. Maybe once in a day or once in an hour, we process the data based on our business requirement. Okay, so these are the two systems. Please do remember this. Now we will be moving into another concept called normalization. With this normalization, we will move into the next concept. Normalization means splitting the data into multiple tables to avoid data redundancy. Okay, you might not understand this term data redundancy. Okay, first let's see an example. Later you will understand that. So this has the diagrammatic representation which will help us to understand easily. Also, let's see. Normalization. Okay, this is taking to another one, normalization in or what? Snowflake schema. I'll tell you what star is. Star and snowflake schema are. I'm just looking for an example where it is showing both the things at a time. Okay, let's take this. Okay, here it is not giving example, it's a general way of representation. I'm looking for a best example. Okay, let's take this. Uh, I'm just thinking, for this, you need to understand what a fact and what a dimension is. Okay, let's see. First, understand what's the fact and dimension table. There are two types of tables. Okay, two types of tables in terms of data modeling, not in terms of database. Database tables are different. They are like permanent, transient, temporary. That's a different story. So this here we have types of tables based on modeling. Okay, facts and dimensions. Facts and dimensions. So let's see what it is. Dimension means descriptive nature describes about something. Let's say we have a product table. Examples. Let's say we have a product table. What it describes, we will have an ID for the product, and this is the description of that product. Product one, ID 1 refers to TV, ID 2 refers to AC, 3 refers to washing machine and fridge, respectively. Okay. Details of product. Basically, the details of product. Or if you're talking about the customer, it describes about the customer. So customer ID, customer name, age, city, all of that. It describes the customer details. So basically, dimensions deals about the descriptive nature of the entities. Okay, describes about something or describes about the entities. Entities means tables. Okay, so now coming to the facts. It holds quantities and measures. Basically, the numerical things, quantities and measures. It doesn't mean that should not contain a dimension. Okay, fact will definitely contain a dimension, but that is all derived. Okay, facts, it holds quantities and measures. Basically, let's say we are talking about an order. That order will be stored in the fact table. That order will have amount. Okay, how much you have spent on that order and how many units you have purchased. All of that details will be available on the fact table. Orders, number of products, price, all of that comes into the facts. Okay, so you will be given a scenario. Maybe in the interviews you will be given a scenario and they'll ask you to identify what is a fact and what is dimension out of that. Let's say you went to market to purchase vegetables. Okay, I'll bring this later. Okay, you went to market to purchase vegetables. This might seem to be very uh, the basic one, or how does the fact, or you might think how does the facts and dimensions fits over here. You went to market to purchase vegetables. You purchased 1 kg tomato and 1 kg potato, 2 kgs onion with some price details. Let's say 50 rupees. This is 30 rupees per kg, and this is also, let's say, 30 rupees per kg. Um, okay, let's assume these are the products you have purchased. Let's say from some store, from uh, Reliance Fresh, maybe. Let's say you have purchased it from a store, Reliance Fresh. Okay, you are purchasing it on a date. Let's say you have purchased that yesterday. Okay, let's make it up. You went to market to purchase vegetables on this particular day and you bought these things. So, out of this table, what are the facts and what are the dimensions? Okay, so let's say here what is describing? We are describing tomato, potato, onion. So, what are these? These are the vegetables. So, we will have a vegetable dimension table. So, with the tomato, potato, and onion. Whatever vegetables are available in the Reliance Fresh, you will only purchase that. Maybe let's say you are searching for cucumber, you did not find it in the store. How will you purchase, right? If the product is available, then only you will be able to purchase. So that you have to maintain a list of products available in this store. So that is the list of vegetables. I only let's say they have only these vegetables. So this is a dimension. Vegetable is a dimension. They'll maintain some IDs. If you go to any stores like Reliance or Ratnadeep or anywhere, they'll be doing a bar scanning of the product, right? That's a unique ID for each product. So you will have tomato as ID1 and some IDs we are maintaining for each of the vegetables. So this is a dimension. Okay, so also now coming to the fact, how much you have purchased. This 1 kg, this 50 rupees, all of that will be comes into the fact, and also this date, on which date it has purchased. It comes into fact table. Okay, so it talks about the numbers. Now let us see. Here we will have the product ID. Instead of the product name, here we will have just the product ID 123, which means tomato, potato, and onion. Purchased on this date 17/4 for all of them. And this is 1 kg. This is also 17.4. This is how the data in the real time looks like. In the fact table, you do not know which is tomato, potato, or onion. You just have the IDs. You have to join that with the dimension table to derive what it means. Okay, so this is of 1 kg and this is of 2 kgs, and price is 50, 30, and 30. Along with, it will also maintain the total value. So 1 into 50, 50 rupees. This is 30, and onion 60 rupees. This is total sales. So this is how we design our facts and dimensions. Okay, now hope you understand what is a what is a fact and what is a dimension. Okay, let's say now coming to the normalization. Let's say I have a product table. Now I'm talking about the uh, product table in the Amazon website. This will have various sections, like let's say I have a product ID 1. This is a TV with some category. What does the TV belongs to? Electronics. Okay. Also I have a category ID. Let's say category ID is 100. 100 belongs to electronics. And I have category number 2. I have purchased a sari. It belongs to, 1 second. It belongs to the category clothing. Okay, clothing or fashion. Okay, let's say ID number 3. I have purchased a lipstick. Let's say this is ID number 3. It belongs to cosmetics. Okay, let's say I have purchased powder as well. That also belongs to cosmetics. So what is the category of cosmetics? So whatever the product is, if it belongs to categories, so it should be the same ID. Okay, let's say I'll purchase shirt. So this belongs to 101, which is clothing. Okay, so now what you are seeing here, these products 1, 2, 3, 4, 5, these are unique. So each product is having each product ID is having a different product. That is fine. But if you look at the category column, it seems to be duplicate one. Okay. ID 103 is repeating. For all the cosmetics, it is 103. For all the clothing, it is 101. Okay, this is called redundancy. If we are uh, having the duplicate data, this is not exactly duplicate, but seems like a duplicate. If we are having a duplicate data in this table, then it is possible to split the table into multiple tables. Okay, so now let's say I want to split this table into 2 tables. One is with the only the products 1, 2, 3, 4, 5. This is a product table with the TV, sari, lipstick, and all of that. I'm not going to write, it is taking time. Okay, now this is a product table. Now I'll here with the product table, I'll just have the numbers so that I'll save some space. It will say like this. Or I'll not have it here. The product category ID, I'll not have it here. It will be coming from the fact table. Let's say while placing the order, it will come over there. Okay, this is a product table and we have a category table. In the category, I'll maintain 101 as electronics. Sorry, 100 as electronics. 101 is clothing. 103 is cosmetics and so on. Okay, so I'll have it in the 2 different tables. Now in the orders table, I'll have order ID, I will have product ID, category ID, amount, quantity, total amount, and order date. Okay, this is how the data comes here. Now here we have order ID. We will know the product ID and category ID. By knowing the product and category ID, I'll be joining this orders table with the product table and category table so that I'll get to know the details. Let's say if they have just placed product ID 1 and category 100, what do I know from that? Nothing, right? If you see TV and electronics, that makes sense to us as a human, right? So these kind of derivations, I mean, in the real time, the tables will be like this. A separate table for product and a separate table for category, another table for orders. And while you are trying to do analytics or making the data ready for analytics, you have to bring them all together. That's your duty. That's our responsibility. You have to bring all of them together. Okay. So which helps some business insights. So that's about the facts and dimensions. There is a lot to discuss about the facts and dimensions still. Lot of types of facts and dimensions. Uh, this is called normalization. Product table, product table containing product and category is redundant. Redundant means duplicates. Not exactly duplicates, but uh, repeated information. Duplicates means repeated information. Okay, is split into two tables, product and category is called normalization. Okay, remember this term normalization. We will use it in our set going forward. Okay, that is normalization. Hope you understand what normalization is. It is splitting the columns, not the rows. Okay, normalization involves splitting the columns, not the rows. Right. Now coming to another concept called uh, data warehousing, or we can call it as another aspect of data modeling. Okay, so now you know what tables are there, how many columns are there in each table, and what are the relationships between them. All of that you know. Now you have to decide whether you want to have all the information in a single table like this. Is the redundancy accepted or not? Do you want the data to be redundant or you want to normalize? So based on this thing, you will have star schema and snowflake schema. Okay. So this is called dimensional modeling. Dimensional modeling because you are modeling the facts and dimensions. That's why it is called as a dimensional modeling. There are two types. Dimensional modeling is of two types. You have to consider all these aspects while designing a data model. Okay. So star schema and snowflake schema. Okay. In both of them, we have one fact table at the center. Let's talk about this Amazon e-commerce website, which where we are referencing the orders table with products, customers, categories, all these details, right? One fact table is orders. Another dimensions are all of these are dimensions: product, category, customers. These are all dimensions. So in either the snowflake schema or the star schema, we will have one fact table at the center surrounded by the multiple dimensions. Okay, let's see in an example here. What this is snowflake schema. Oh, I think they have not given a diagram. Let's see. Star schema. Okay, let's see this. Okay, in the star schema, we have one fact table. In the images, while highlighting, they are showing the all the attributes, but while expanding, it is not giving. Visit this snowflake star. I'm looking for the actual table names in the star schema. Okay, let's see this. Okay, first focus on the star schema. We have one fact table. Uh, this is sales fact. We can refer it as sales table or the orders table. Anything is fine. Okay, the sales table. which is talking about the Amazon sales. They will have customer base, because if there are customers, then only the purchases will happen. And we have a products table, which lists down the list of products available. And the sales channel. Channel means either online, offline, Amazon, Flipkart, Myntra, whatever it is. This is the sales channel. And geography. Geography means the location. Is it the location of the product or location of the customer? It refers to anything. Okay. So here we have a single fact table surrounded by multiple dimensions. Okay, single layer dimension tables are directly connected to the fact table. So now coming to the another aspect, the sales table. In the Snowflake schema, we have a customer table. The customer table containing customer ID, customer name, and also address. Okay. In instead of address, let's say I will have it as a, country name, state, city, village, and then zip code. I'll have that level of information in the customer table. So instead of maintaining that, what I'm doing is, for the customer table, I'm splitting that into multiple tables. Customer type and the customer region. What is customer type? Let's see customer type later. But the customer region. What doing is, I'm just maintaining IDs in the customer table for the address, and maintaining that address in a different table, just like how we did for the product and category. Let's say this customer table containing customer ID, name, state, city, sorry, country also required. Country, state, city, zip code, city, or let's say colony or a village, and zip code. This is the information we have it here. Now what I'm doing is, instead of having all of this in a single table, I want to have the customer table having customer ID, name, and address ID. Okay. This is the customer table, and I will have an address dimension containing address ID, country, state, zip code. Okay. So by joining these two tables on the address ID, I'll get to know the details. Okay, I'm splitting that in. That's the meaning of normalization. We have now, the customer table is now normalized in the Snowflake schema. It is split into the customer type and the customer region. I don't know what they are meaning to the customer type, maybe online, offline. Let's see that later. And now coming to the product table. We are splitting that into, let's say, in our product table, we have just a TV, where it is. We have TVs array lipstick. Let's say we also have the brands here. Samsung TV, or some Nika lipstick, or some Pond's powder, or some Arrow shirt. Okay, we have some brands here with the brand ID. So it is possible to split the brands and into the electron brands and the categories. It is not definitely needed to split into two tables. We are just categorizing that. So let's say if you have taken the product table, single product table, it is split into product and the product category. The customer table, it has split into customer and the address table. Okay. Similarly, the time. Let's say in the real-time projects, we will have a date dimension table. Instead of referencing the order dates or the purchase dates directly, we will have a order date dimension. Sorry, not order date. We will simply have a date dimension, where we will have date ID, date, year, month, week, quarter, and lot of other details. Day, name of the date, name of the month, name of the week. There will be a lot of other details. Okay. So the complete calendar starting from, I think, 90 in databases, they'll start from 1970 till 999 this year. So all these information will be stored in the date dimension table. In the real times, you will definitely see a date dimension table. So in the tables, maybe in the orders table or the customers table or wherever it is, we are referencing the date. Instead of actually referring the date, they'll refer date ID. Based on this date ID, you have to get it from the date dimension table. That is how the real-time projects will work. Okay. So that is what they are splitting. Now they are splitting that date table into time and quarter into two different tables. So now what is the advantage of splitting that or combining that? Okay. So if we are, let's say in case of star schema, one fact table surrounded by multiple dimensions. Here if you take this is 5 dimension tables. Here if you see each table is split into the two tables. Maybe we have around 8 tables here. Okay. So joining 5 tables versus joining 8 tables, which you feel is more comfortable? Obviously joining the 5 tables because we have less number of tables, all data at a single place, easy to join, easy to derive results. In case of snowflake schema, we have to join lot of tables. Okay, and we have to join lot of tables. That joining becomes complicated and it might even lead to performance issues. Okay, and why do we choose each of this? When to choose and why to choose each of this? If you are working on a reporting project, reporting means you are preparing the data for analytics. Most of the times that is what as a data engineer we do. We design our data ready for analytics. So for, if we are trying to build the reports, star schema is efficient. Okay, but what are the limitations of the star schema? The data is redundant, so it will increase the storage cost. Okay, the data is redundant, it will increase the storage cost. That's the only limitation of the star schema. And the data is also redundant. And in case of snowflake schema, the storage is efficient because we are not storing redundant data. The storage is efficient, but still we have to maintain lot of tables and the integrity between them. Integrity means the relationships between them. Okay, so the address ID should strictly follow. Each address ID should have a unique address. So all those integrity things we have to follow. So let's see the structure. Central fact table is connected to normalized dimension tables in the snowflake schema, which are further connected to sub-dimension tables. Okay. So these dimensions, there is also a scope that these dimensions are again split into another dimensions. Okay. So each is fact table surrounded by multiple dimensions. The dimensions are normalized. Those normalized dimensions also might be split into further small tables. Okay. So the central fact table is connected to the denormalized. Denormalization means combining. Normalization means splitting. Denormalization means combining. Okay. Lower data redundancy. Redundancy means duplicacy. In case of Snowflake, we have less. Here it is high. Data integrity. Higher data integrity because of data normalization. Integrity means the relationships and ease of what we can say governance. Integrity means the data is strictly deduplicated. Now the duplicates are not there or redundancy is not there. So that is the meaning of integrity. We are strictly following the relationships one to one, one to many, many to many. We are strictly following those kind of relationships. Okay, that is called the integrity. More susceptible to data anomalies upon improper management because in the sales state, in case of star schema, we have multiple entries for the same ID. Let's go here. Let's say we are taking this ID. We will have multiple entries. Let's say our intention is to join on powder. Okay, I want to get powder, but unnoticingly or accidentally, I did not see there is another thing which comes into cosmetics. I did not observe that because of the huge volumes of data I have overlooked, and now I am considering that only 103 means powder. So let's say I'm doing aggregation for the 103, the count of products for this. You might end up in getting more numbers because that is a count of both lipstick and powder, right? So you might end up in counting both of them. So that is where we are missing integrity in case of star schema. But in case of snowflake schema, for 103, there is definitely only one product that is related to another thing here. We have to join that. Only after joining, we will have a different product ID for even though the cosmetics is same. So that is the meaning of integrity. Storage space in Snowflake schema, sorry, uses less storage because the tables are normalized, no duplicacy. It uses more space because more redundant data is stored in the tables. And in coming to the performance, Snowflake is less performance because there are a lot of tables to join. Okay, it is faster because less joins but more storage space. Use cases: high data integrity, detailed hierarchical analysis, and minimal data redundancy. When you want high integrity or detailed analysis, then go for Snowflake schema. Otherwise, just go for star schema. Faster performance, ease of use, and simplicity. So both of it has its own advantages and disadvantages. So depending on our requirement, we have to choose. Mostly for reporting purposes, we'll go for star schema. Okay, I'll paste this link for the star and Snowflake schema so that star schema versus Snowflake schema. Okay, let me paste all of this in the normalization concept. Okay, so okay, so mostly we have talked about OLTP and OLAP, right? OLTP systems follows normalization or the Snowflake schema. Normalization or Snowflake schema in general. It's not a strict and hard rule because this is write heavy operations. If the table is containing huge volumes of data, it would be difficult to write into the table. Okay, let's say your cupboard is already filled with clothes. You are still trying to fit the others. It would be difficult. So you will sort that. You will split that. So that's it. Here in case of OLAP, we go for star schema in general. Okay, so that's about the star and the Snowflake schema. You can go through this documentation. You'll get to know a lot of details. So, but overall, this is what we have discussed. Now, now we are left with types of facts and dimensions. Okay, first let's see the types of facts. It's a quick one. Types of facts. This is snapshot fact table, and we have additive facts, semi-additive facts. You no need to really bother about these types of facts, but just have an idea. Semi-additive and non-additive. By looking at this, additive means generally, basically, or the fact table means it holds quantities and measures. So some of them we will be able to add them, some of them we will not be able to add them. So let's say uh, this tomato, potato, these quantities we can add it. Somewhere I have written these quantities we were able to add them. Okay, but these dates we will not be able to add them. Okay, so depending on how if you are able to add or not, they are classified into additive, semi-additive, and non-additive. Let's see. Let's close all of this. Nobody is going to ask you about the types of facts, but have an idea. There are various things. Okay, let's focus on this data warehousing metrics. Additive facts. Data that can be added across all the dimensions, such as total sales or the total sales amount. Dollars means amount. Okay, semi-additive data that can only be added across some dimensions such as bank balances can be added by account, not by time. What does it mean? If we have like banking details, let's say our data is for banking application. So if you want to calculate the balance of a customer, you have to calculate for each customer or each account ID you have to calculate. not by the year, not by the date, right? So that is called semi-additive. We are partially able to add it. We can add through a day, year like that, but that doesn't give a meaning. Okay, when we are calculating balances, that should be per account. Okay, this is called semi-additive and non-additive. Data that cannot be summed up, such as percentages, ratios, or unit prices. Okay, you might be thinking why we cannot do you sum on the unit prices. You can do the sum on unit prices, but what is the derivation or what is that output you are trying to get out of that? Nothing, right? So I'll say the cost of the powder is 100 rupees, the cost of sari is 1000 rupees. If you sum up all of that, what you will get? You don't get nothing. It is not that those two products are purchased by a customer. No, it's not purchased. It's a dimension table, or sorry, not a dimension. It's a fact table containing this list. If you do the unit sum of that prices, you will not get any information. And we have something called factless fact table. Yes, this is important. Factless fact table means it doesn't hold any quantities or measures, but still it is called as a fact table. So the example of that is the attendance of the student. Okay, it says whether present or absent, but there are no numerical measures. That is called a factless fact. Tables that record interactions like the attendance that do not contain numerical measures. So let's put it down. These are the types of facts. Okay, snapshot fact I have given you additionally. What does it mean is, let's say our business is running for the last 10 years. Okay, we have all that data in a single table, which makes operational heavy. Because while we are trying to write the data or query the data, it becomes heavy because of the volumes of the data it has. So generally what we do is we create snapshots. So maybe for the year 2022, I'll split that into a separate table. Or for the last quarter, I'll maintain that as a separate table. That is called the snapshot fact table. Mm, taking a copy of data, for a certain time period into separate table. This you will see in the real times. We'll be taking copy of the data. Maybe business will request us. I want the data for the year 2024. Please provide it. Instead of giving the whole table and asking them to write queries on top of that, we will create a separate copy with all the filters and then give it to. This is the snapshot fact table. Okay. What is this helical? Okay, I will stop it here. Mm. Is it okay if we continue tomorrow as well? Or today itself we can extend a little more? What do you say?
Anything is okay for me.
Okay, so let's see the types of dimensions then. Types of dimensions are really important. Facts we are not bothered about much, but dimensions, it's very important. Okay, so types of dimensions. We have around 5 or 6 types. Let's see. Out of which only one type is more important, and in that also we have subtypes. Types of dimensions. Okay, let's look at the types. Okay, so these are the important types. All of these are not important, but generally what we use, let me tell you. Slowly changing dimension. This is extensively important, very important. So other things we are just going to discuss theoretically, but this slowly changing dimension, it is implemented in every project. There will not be a project which is not using a slowly changing dimension. Okay, so if you don't know this slowly changing dimension, it would be very difficult. Okay, the other things, even if you know or don't know, it doesn't matter. So, but slowly changing dimension is very, very, very important. Let's make it stars. Okay. So first we'll see the other things. Later we'll come to the slowly changing dimension because that's a time-taking concept. Let's talk about slowly changing dimension later. Okay. This is role playing. Regenerate. Okay. Conform a dimension. Let's see here. A dimension that can be used by multiple facts and has the same meaning across the model is called a conformer dimension. Uh, what it means is we will have a dimension table, let's say the location table or the geography table, which contains country, city, state, and the zip code. Okay, if that table is referred in the customer table or the um, orders table, so anywhere if you are referring, the meaning is same. It is just the location or the address. Okay, location. It will be little confusing when I'll tell you one more concept, role playing dimension and conformer dimension. Okay, so here we are giving example. If we have a dimension for the list of places, this can be used across multiple facts. It has the same meaning. A dimension that can be used by multiple facts and has the same meaning across the model is called a conformer dimension. Just remember this example, the list of places, wherever we refer this place, it will be place. The meaning is same. It will be the place. Okay, this is the meaning of conformed dimension. The meaning is fixed. Conformed means fixed. Let's paste it here. I'll also paste the link. Okay. So now the degenerate dimension. Each dimension having the equal importance. So let's say when a fact table stores dimension values, not foreign keys to the dimension tables, then we call it as a degenerate dimension. So usually, if a fact table, generally what does fact table holds? It holds the dimensions, but they are all foreign keys. If you look at our this orders table, where is it? Orders table, this product ID, category ID, or maybe the customer ID, address ID, all of them are foreign keys to this table. Only order ID is the primary key. Okay, so that's why they are explicitly referring, not foreign keys to the dimension tables. So if we are storing a fact uh, sorry, if we are storing a dimension in a fact table, then we call it as a degenerate dimension. Usually, if there are independent dimensional attributes, then they are stored within the fact tables. A typical example of this is a invoice number. When you purchase something on any website, Amazon, Flipkart, anywhere, you will get a invoice. Okay, invoice for every order. Okay, so that is independent of anything because that invoice contains your purchase details along with the order of purchase or maybe if any warranty applied. So it is not related to any of the other attributes. So that is called a degenerate dimension, which is an independent dimension. Independent dimension stored in the fact. Let's paste it here. Don't worry, nobody is going to ask what a degenerate dimension is. Most of the times, maybe they'll ask conformed dimension, role playing dimension, and a junk dimension. And definitely the slowly changing dimension. That's a default thing. Even if I don't say, remember that everybody is going to ask you slowly changing dimension because that is what we use it in the real time. The other dimensions we might use it, but we might not refer, especially like this is a degenerate, this is that. We do not especially maintain that kind of things. Okay, now the junk dimensions, which has unimportant data. Okay, if the model has too many small dimensions, then all of them can be put into one dimension, though each of the small dimensions is unrelated. Okay, some unimportant data. Maybe they'll ask you this as well. When we store some unimportant data, we call it as a chunk dimension. Maybe the attendance of the students. That also comes under the factless fact. Let's see an example of the junk dimension. Example of junk dimension. Okay, a junk dimension is a modeling technique that combines low cardinality. Cardinality is another term which I have to explain, which says either true or false into a single dimension table. So junk dimension space, it has very less number of values, either s or no, true or false, like that. Okay, let me write true or false, yes or no. These kind of things we store it in the junk dimensions. So when it comes to cardinality, let's write here low cardinal columns. Cardinality means the number of distinct values in that column. Okay. Cardinality. Low cardinality means less number of distinct values. High cardinality means more number of distinct values in a column. Cardinality means the number of distinct values or the unique values available in a column. I'm saying available in a column, not on a table level. It's on a column level. Okay, if you say take the customer table, I'll have customer ID, customer name, gender. Let's say these three columns. What is the cardinality of the customer ID? It would be high because each customer ID is having different IDs. So cardinality of that customer ID is high. But if you talk about the cardinality of the gender, it might be male, female, or very hardly others. Okay, only three values. So that is a low cardinal column. So let's write here customer table ID is high cardinal, gender is low cardinal. Okay, this is the meaning of cardinality. And we have another term called granularity. Granularity, which means the level of details. Okay, granularity means the level of details. Let's say we are talking about some aggregations. Let's say we are building some reports. What level of details does it have? Is it on a product level? Okay, for each product, what is the information we have? Is it for each product we are getting the aggregate, or each weekly, or quarterly, or monthly? How we are getting it? Quarterly or monthly? What is the least level of information that is available? Okay, granularity is level of details, or we can say least level of information. Okay, this is called granularity. See with an example. Granularity. Granularity of data. I'm looking for example so that you will catch it easily. Okay, let's see here. This is some corporate data with customer, gender, phone. These are for each customer, they are maintaining an information. For each customer, a corporate company is maintaining the customer information like customer level. This is the least possible level at which they can maintain. Another level, what they can maintain is, let's say city wise, okay, or for each zip code wise, how many customers are there? For zip code 1, there are 20 customers. For zip code 2, there are 50 customers. All of them are males or females. So that is another level of granularity. Granularity at the zip code level or the area level. Or let's say I'm now going by the country wise. So country wise population. Okay. India has 131 crores, let's say, and China has 130 crores. Let's assume. So for each country, we are getting the population. The minimum information we have it is minimum level of information is country wise, or maybe we can maintain state wise or city wise. So what is the minimum level of information we are maintaining? That we call it as a granularity. Okay. See what is this doing? See granularity, order ID, product name, subcategory, category. What is this level of detail? Okay, order. If you talk about the e-commerce website, if you are maintaining order details, so order ID is the minimum level of information because each order ID is a separate transaction itself. Okay, but if you talk at a category level, let's say on the category level, I have fashion. Inside the fashion, I might have footwear or clothing or cosmetics. That comes under the subcategory. If you see here, this is giving a lot of information. This image is giving a lot of information. Granularity. So this is more granular. Order ID is the minimum level of information. So that is called more granularity. So as you go up in the hierarchy, category, if you are talking about category, maybe electronics, fashion, jewelry. So that is a category level which is giving less amount of details. If you're going at the subcategory, so it might give you more details than the category. Or if you go at a product level, it might give us more details than the subcategory. Or if you go to the product level, it will give the complete details. That's the meaning of granularity. Here, see, category is a higher granular and this is a lower level of detail. So the level of details we call it as a granularity. So that's about the two terms we have. Now coming back, the role playing dimension. So you might feel confused about the role playing dimension and a conformer dimension. Let's see. A role playing dimension consists of values that can be associated with multiple facts. For example, the sales location, product location, person location can all be related to a single place dimension. Earlier in the conformer dimension, we have seen the list of places where it is, yeah, the list of places. It has the same meaning across multiple facts, right? It is referring to the same information across the multiple facts. Here also, it is referring to the same thing, but we have a location table. We are joining that with the sales table, then that becomes the sales location. If the location table is joined with the product table, it becomes the product location, and if it is joined with the customer table, it becomes the customer address. Okay, all be related to a single place dimension, but in changes in meaning to the context. So this is all place. There is no doubt this is definitely a place, but it is changing its meaning based on the context. Okay, another example of this is date dimension. So if we, I said in the real times, we will definitely have a date dimension and date IDs are referred in the actual tables. So if we are referring the date in the orders table, it refers to the orders date. If we are referring that date in the shipment table, shipment means the delivery. Okay, if it refers to the delivery date. So or it refers, if it is referred in the employee table, let's say employee table. Employee means the delivery boy of the Amazon orders. Let's say that date becomes the hiring date of that employee. So it is changing its meaning. Depending on the context, it is changing its meaning. The same dimension playing multiple roles, that is called the role playing dimension. The way we look at it is different. So ideally or strictly speaking, conformed or role playing, it's the same, but the way we look at it is different. That's the meaning of role playing. Okay, static dimension. These are not going to change ever. Like the gender columns, male, female, others. There is no other category. They are all static. It never changes. Okay. Or the attendance of the students. It might be present, absent. Only two. It is never going to change, whatever the reason is. Static dimension means fixed dimension. They are not going to change ever. And we have shrunken dimension. Let's see. If a dimension cannot be further divided into small, it is called a shrunken dimension. I mean, it's a minimum level of information. See here, an example of this would be a product dimension that is further snowflaked into product category and dimension. We have already seen this. The product table, we are able to split into the product table and the product category table. So further, if you want to split it, is that possible? No, right? So if the table is not able to be split further, then we can say it as a shrunken dimension. Okay, this is shrunken dimension. Okay, so this is all about the other dimension types. Now coming to the slowly changing dimension, where it is. Okay, this is extremely important. In itself, it has 5 or 6 types, but all of them are not required. We need type 1, 2, 3. The first 3 types are very, very important. Okay, first understand the term slowly changing dimension, which means it changes over a period of time. It doesn't change overnight, but there is some frequency or that is not expected. Okay, let's say we have a customer table or an employee table. Currently, he is in Hyderabad, let us assume. Customer is in Hyderabad. Maybe 2 years or 5 years down the line, he might shift his address because of various reasons. Maybe he has purchased his own flat, or maybe his job is in other location, or his children is there and they got some admission into a big international school. Whatever might be the reason, he is changing his address. How frequently or how long it is taking to change that address? It is not definitive. We cannot say maybe he might shift in 1 year, he might shift in 1 month, or he might not shift in the 5 years, or it might take 10 years for him to shift, or he might not change at all in his lifetime. It is indefinite. We cannot say this is definitely going to happen, but there is a scope. It may happen or it may not happen. Okay. So whenever he is changing his address, how do you want to deal with that kind of changes? Let's say the customer ID one, mm, locate, locating in, sorry, staying in Hyderabad, let's say from 2020 to current date. Okay, to current date. So in general, in the real time, the current, if we are not sure about the date uh, till which that is applicable. Let's say this customer is in Hyderabad. I don't know how long she will be in Hyderabad. In those cases, I'll be maintaining this as the calendar date. This is the maximum date of a calendar in any database we consider. Okay, which means if you see this kind of date, don't get confused, meaning that it is the current active record. Okay, this is the current address of that person. Let's say the same customer uh, after 5 years shifting to Chennai on some date, let's say today's date. I'm shifting, okay, to Chennai because I have got a new job. Let's assume I'm shifting to Chennai on this particular date. So this is in our target table, in our database, this is the information available. So every day we will get the information from the source also. Okay, there will be a source file, there will be a target table. Let's say yesterday we have loaded the table into, sorry, I think I forgot to show you that, but the table is loaded into the, sorry, the file is loaded into the table. I'll show you. Uh, in the real time, everything we get it as a files, not definitely a file, but most of the times we will get the data in the files. So from that file we have to convert that to a table, and we have to identify what is changed, what is not changed. If this is a new customer, let's say this is our target table. Okay, right now that is our target table, and this is our source. On the target table we are getting a new customer, ABC. Location as Hyderabad with some date. Okay, that person started staying in Hyderabad starting this date, and we might not get this end date. Okay, we have to infer that. Okay, this customer is not available. I have to insert that into our target table. The customer ID 1 is already available, but it looks like they have changed her address. Okay, I have to take these two things into consideration. First of all, let's go one by one. First, I am worried about this change in the address. Okay, so in how many ways we can change that? Let's say now I will directly join these two tables and I will directly update address equal to Chennai. Okay, for some time forget about these dates. Sometime forget about that dates for a while. Okay, so this is our target table. Let's assume this is our target table and this is the data now coming from the source for that particular table today. I see that ID is matching, name is also matching, which means this is the same customer, but looks like the address is changed. So I directly go to this table and update address equal to Chennai. Now I'll remove this. This will not be there any longer. I'll just have this one record, which is Chennai. I don't know where she was residing previously. This level of information is not available. This is one kind of update. Remember this. This is one kind of update. Another thing what I can do is I will have this start date and also end date. Okay. Start date and also end date. Whenever there is a new entry coming in with this as the start date. Okay. So what I want to make is for this existing record. Okay. For this existing record, I have to update the end date. So in Hyderabad, till which date she was in Hyderabad? Till yesterday. Before this date, she was in Hyderabad. So 2026 4/16, she was in Hyderabad. Now starting today, she is in Chennai. This date I don't know. In future when she will change, I don't know. But for now, this is the active record, active location where she is residing. Okay. I'm maintaining two entries for this record now. I'm updating the old record with the end date and maintaining a new record in the same table. We have two entries now. By looking at this date, you will know currently at which city she is in, right? So along with this, we will maintain an indicator which is active or inactive. So initially this would be active, okay, maybe true or false or 0 or 1 or active inactive. There are various ways people use. It all depends on how they have designed their data warehouse. I'll go with active inactive. So initially it was active. Now we should make it as inactive and the new record should be marked as active. Okay, this is another way of storing the information. Okay, let's see. There are still a lot of ways. Okay, she is in Hyderabad first. This is my table. Assume that this is my table. And now you see there is a new change. She is in Chennai now. You are getting the data from the source like this. Okay, so here you will maintain in the table how you will maintain this information is I'm showing another way of maintaining this. I'll have this record only one customer ID, but this would be previous address, and here we will have one more address as current address, which says Chennai. Okay, so this is another way of storing it still. Okay, now this is the active record. Okay, this is the active record. This is in a older record or the historical record. So I'll maintain this whenever a new data is coming. Only this should be there in my target. Okay, this should be moved to historical table. This shows move to historical table. We will maintain two tables here. We will maintain that record in the history. Maybe we will maintain the dates or we will not maintain the dates. Okay, so here this would be the active table or the current table. We will maintain history in the separate table and active data in a separate table. Okay. So these are the important ways in which we are storing the data. Now coming back, so this is type 1. We have discussed the concepts. Now we are segregating into the various types. Directly updating the data without storing history. Okay. Previously it was Hyderabad. Now I have updated it to Chennai. This is type 1. Okay. Direct update without history. Okay. This is called type 1, SCD type 1. And this we call it as we are maintaining history along with start and end dates and active flags. This is type 2, which means maintain history with active flag along with time period. Active flag along with the time period. This is type 2. So in the real-time projects, people extensively use type 2. Everywhere you will see the type 2 dimension. Most of the times we see very rarely the type 1 also used, but most of the times it would be type 2 dimension. Okay, because they want to know history. Why history is preserved? Let's say we have loaded some data. Let's say our project is running for the last 10 years. Now this person changed address. For some reason during this time period, there was an issue with the data. I want to update the historical data. So if I'm not maintaining this history, for this particular time period also, address will be shown as Chennai, right, which is incorrect. So in order to maintain the historical updates or the backfills in the real time, we need to do lot of historical data fixes. There will be lot of bugs will be there. We need to fix that. So for that reason, we will be maintaining the historical data as well. So they might be asking why you need history. Anyways, this person is not there. That is not his current address. Why do you need it anymore? Why are you wasting the space? They might ask you or they might question you. This is because in the future we might need to fix the historical data. So which gives us incorrect data if we are maintaining only the latest record. We should have an agreement with the business. If they ask you to delete the data, you have to explain the scenario. Okay, you are telling I will delete it, but in the future you may face these consequences. Whenever you are trying to update the historical data, you might see this person's address as Chennai, which is incorrect. Okay, we have to tell them the consequences. Based on that they will decide, because business, they are not the technical people, they are the ones who is owning the business and who is getting the money. We have to make them understand these are the consequences, these are the benefits, these are the disadvantages of maintaining so and so data. Okay, then they might not understand what type 1, type 2, type 3. You might directly go and ask what type of SCD you want. They don't understand what type of SCD. You have to take the data and explain that, then only they'll understand. Okay. So this is the type 3 where we maintain the previous and the current address in the separate columns. Type 3, or we can say it as a maintain limited history. So let's say this person changed the address another time. So to Bangalore. So we might store only the previous and the current values. Maintain limited history with additional column. When I say limited history, current and previous values. Okay. So, and this is type 4, history stored in separate table and current data in target table. Okay. So this is about the slowly changing dimensions. So type 1 and type 2, we use it frequently in the projects. Type 1 rarely, but we do direct updates to the data. And type 2 is extensively used in the interviews or in the real time. You have to write queries to implement type 2, SCD type 2. Okay, let's come here. Some documentations, they'll also give the type still type 6. Here they have given only till 3, but these are enough. Whatever I have explained so far, that is enough. Those types are enough. Okay. Uh, let's see. Somebody might refer to it as also type 0. Type direct update. Let me tell you. Type 0, we will have type 0. Where did I write type 1? Okay. Okay, type 0. No changes at all. Okay, no changes at all. Let's say the gender columns. So the person cannot change his gender throughout his life, right? Now the technology is there, but ideally speaking, the gender cannot change for a person. He can change his address, he can change his name, but he cannot change his gender, right? So that's type 0. STD types. Okay, see here. Okay, type 0. It is fixed. Date of birth, it is never going to change. Type 1, old data is overwritten with new, no history is maintained. Just we are replacing Hyderabad with the Chennai. And type 2, we maintain versioning. A new record is created with the new version, making the old version as inactive. It tracks the full history. Okay, we have already seen that. See here, version means the different historical data. Active, inactive. Let's say in the future he might change after an year. Now this date becomes 1 day less than the shifting date. Okay, and we will have one more record with the start date as that date after 1 year, and the end date would be this maximum in a calendar, and this would become inactive, and we will insert one more row with that will be the active one. So there is no restriction that he can change only once. No, he can change any number of times, but all the historical records will be updated as inactive, and only the recent one is active. And coming to type 3, it adds a new column to store previous values, keeping the only the current and the immediate previous. I said right, limited history, only current and previous values. In type 4, it retains the current table, moves all the data to a separate historical table. Yes, history is maintained in separate table and only active data is maintained in the current table. So there is type 6, which combines type 1 to 3 approaches to track history while allowing easy current state provisioning. So generally we don't go for type 6. Use first as requiring the best of 1, 2 and full history with ease. So generally we don't maintain this. Here what will happen is we will maintain history in the separate table that is there. Also we will maintain current and previous records in the current table along with the dates. Everything is mixed together here. Okay. Everything is mixed together in type 6. Generally we don't go for this approach. Okay, that's about the slowly changing dimensions. Let's try to implement that. Okay, let's open our database. So once we implement this, I'll stop the session so that we are good with the data warehousing. So in our next session, we will start Snowflake. Please explore on your side as well because you will get to know a lot of things when you are exploring. It is not responding. I'll take our employee or the customer table. Let's see. Based on the data, I will see. In the real time, we will be getting data from the files. That file, we have to load it into some stage table first. A stage table means which is going to truncate and load every time. Okay, which is not exposed to business. Stage table means an intermediate table uh, built for some ETL purpose. Okay, you know ETL means extract, transform, and load. As a part of building those pipelines, we need some intermediate tables. Those are called the staging tables. Okay, let's see. I'll take our customer table. It is still connecting. Wait a second. Please let me know if you're not able to follow or if you have any questions so far. Okay, it is still connecting. So let's start from, let's say, DE training, DBO schema, and the customer's table. Let's see the data available here. Okay, nothing. Let's look at DE schema. Okay, so we have some data here. I'll maintain another table. Generally, in the real time, we will have the file. That file will be loaded to the table first. Another table, not directly to this table. That table will be loaded to the stage table, and we will join that stage table with the target table and do the updates. Let's create a copy of this. Let's say, mm, I'll tell you the few more concepts here. Anyways, as we are discussing, create a table, customer. I'll maintain it as source customer. Okay, this is the source data. I just want to create the structure like this table. I just want to create the table, not the data. Okay, let's run it. I'm not sure if this syntax works here or not. What is happening? Executing query. Correct the syntax here. Like, let's write in the brackets. Like means it will just copy the structure. Uh, so each server behaves differently. So a little confused with the syntax. Let's see this. Structure only, but this is not working. Like this table created syntax error. Use double quotes to wrap the table names. No, that is not required. MS SQL, Microsoft SQL Server, I mean to say. Hmm. Okay, Microsoft SQL Server doesn't support the like syntax. We definitely have to create a table. Let's see. Select the star into this source customer from the target customers. I'm just trying to replicate the structure of the table from the target table without the data. Let's say with a limit 0. Okay, here limit is doesn't work. Select the top 0. Let's see this. Okay, so the table is created without any data. Let's remove this. Yeah, I'm just trying to create a structure. Select star from this source table now. Okay, every day the source table gets loaded and deleted. Okay, right now we do not have any data here. Let's look at the already available data. I'll cover incremental load also. along with the SCD. Okay. See here we have the customer IDs. Some customer IDs are already available. Let's say intentionally I'm inserting some data into the source customers. I'm preparing the source data. Okay. So in the real time, you no need to prepare the source data that already comes from the source in some of the files. Here I am preparing it from uh, this customers table. Okay. So let's say I'm inserting all the data into the source table. Let's do insert into now. The table is already existing, that's why it was not allowing this. Insert into direct star from. So this is another way of inserting. We are inserting data from one table into another table. This is how we do it in the real time. Okay, 7 rows affected. Now both the tables have the same data. Okay, both the tables have the same data. I'm going to insert few more rows into the source data. Okay, source data. I'm going to insert few more rows. Insert into. It's like we are getting new customers. Values. Let's bring this down. I'll insert two more customers. Customer ID 1, 2, 3, 4, 5 is there, 6. Let's insert customer 6. What are the names? Let's see. Okay, customer ID 6. Location, age, country, state. Okay, I'm inserting. I'll insert one more row, 7. Let's see. And my, and my age 26 and country is India, state is Tamil Nadu. Okay, I'm inserting two rows. Now, if you see, the source table has two additional rows. Where is this? Let's copy these two. I'm explaining you the real-time scenarios. Okay, please focus. This will also be asked in the interviews and you have to really implement it in our projects. Okay, now the target table is this one, DE schema customers. The customers has 7 rows and the source table has how many? One second. The source table has 9 rows, out of which 7 are common between them. Okay. And one more thing I want to tell you, if you want to know the rows available extra in the target or extra in the source. Let's say now we have extra in the source. And I want to know what are those extra things. Okay. For that we have to do minus. This minus will give the extra rows from the first table. Whatever you are doing, if you are doing a minus, it will give extra data in the first table which is not in the second table. It will compare all the columns. Even it finds a single mismatch, then it will return the complete row. Okay, sorry. Why is it giving? Why 2 we are getting 2? Maybe minus also doesn't work here or what? Second, let's run this. Okay, 7, this is fine. What happens if I'm running these two? I think minus is not supporting here. First table is having 9. Second table is having 7. Okay, minus is not working. Generally, this minus will give the additional records in table 1. MS equal. Please be aware of this concept. It is supported in most of the databases. Okay, here we have except. In Microsoft SQL, we have except, but in other servers, it is minus. So we rarely use this server in the real time. That's why I'm using the other keywords. Okay, so except. You can see here, now the ID number 6 and 7 are not there in the source table. That's why it is giving them. This is one way of identifying. Or if you want to have the common rows between the two tables, you can do an inner join, or the other way is intersect. I don't know if intersect is available here or not. Yes, it is there. Intersect means common. Let's write here common rows. If there is difference, even though ID and name are same, if there is a difference in the location or any of the other values, it will change. Or you have to do just select the required columns on which you want to find the difference. Let's say I just want to know the IDs. These are the common things. Okay, I just want to know the difference only in the IDs. I want to know the employee IDs, sorry, customer IDs who are not there in the target. So that even though if we have differences in the other columns, it will be ignoring. So you will just get these two IDs, right? So this is the way to identify. Okay. So now we are not going to use minus. We can we can do that. Okay, let's first do that with minus. Okay, now what I want to do, I want to insert this additional data into the table. Insert into this customers table. Okay. Select the star from the source table. I don't want to insert all of them, right? I want to insert the rows which are not already there in the target. How do I get that? By using except select star from the target table. Okay, but I'm not going to directly run insert. First, I'll see this except am I getting the expected data or not? Yes, these are the two rows I want to be inserted into this table, right? So now let's run this as a whole. This table before insert has 7 rows, remember. Okay, 2 rows affected. Select a star from this table. You will get ID number 6 and 7. Okay, now we have 2 additional rows inserted. This is called incremental load. Incremental load means insert the data whichever is not available already. Okay, so in the source files, every day you might be getting the data which is already existing along with some new data, but into the target, you want to insert only the fresh data. That is called incremental load. Let's write here. They'll ask you what is incremental load and in how many ways you can do it. Incremental load, or we can also call this as delta load. Whatever the term is, it is inserting only the new data which is not already available in target. Source might have all the data along with new data. Okay. So hope you understood the incremental load. So this is one way of doing this, but this except it is not a ideal way to use it. Okay, except is used whenever you want to know which data is not available. That is fine. Identifying is fine, but while inserting, it is not a best practice because it leads to performance issues in case of huge volumes. So we generally don't do this. So how we can do is now into the source table, let's insert few more rows. Where is this insert statement? I'll insert 2 more rows with IDs 8 and 9. 8, sorry, 9, Uh, let's see the names. Okay, I'll keep the other details. Don't worry about that. Okay, now my source table. It is another run, getting two more rows. Let's take this to the end. It is telling, I don't know why is it taking a lot of time to insert only two rows. Let's stop it and rerun it. Okay, it is cancelling the query. Let's right select start. First, let us see if it is inserted or not. It is still running. Let's save this. Meanwhile, I'll save this data modeling as well. Text file. Yeah, let's save it as SCD incremental. SCD and incremental. Okay, let's see if this is cancelled. The two rows affected, but let us see if the data is inserted or not. It's taking a lot of time. Let me open a new query. Okay, we have got the data here. Now the source table is having 11 rows and the target will have only 9 rows. Let's see. Target is having 9 rows. Assume that this customer ID is the primary key. Primary key means no duplicates, no nulls. I don't know, for some reason this is very slow. Maybe I have to restart. Let's save this first.
It's overload to system and it's overload to me as well.
Okay. We are almost about to wrap. I'll complete incremental and we'll discuss SCD
Yeah.
tomorrow. SCD is little complicated. We are almost there. Just insert these two rows and we will wind up. Okay, so now we have 7 rows in the target. Sorry, 9 rows in the target and only, sorry, 11 rows in the source. Let's insert into that. Insert into this target table. Okay, what do I want to insert here? Select a star from the source table. Okay, select star from source table. What I want to select, okay, whichever rows which are not available in the so target I want to insert. Okay, first let's write the join. Left join with the target table. I'll maintain it as T and this as S, which means source and target on test dot customer ID equal to C dot customer ID. Okay, let's see what you will get now. So I'll want to get the data from the source. Okay, let's get all of that so that it would be good. Could not be found. Why? Let's see, the column means it is customer ID. Okay, this is not C, it is T. Okay, we are executing only 9 rows, still taking a lot of time. Hmm. I just want to complete these 2 rows, then I'll wind up. Okay, how do you get these 2 additional rows? This is from the left table, S table, and this is on the right table, T table. So if I apply a customer ID null on the right table, then I will get only these 2 rows, right? So let's apply where T dot on the target side, customer ID is null. Okay, so this is what I want to insert into the target. Let's first confirm these are the 2 rows. Yes, I don't want the right side ones, right? So just select S dot star. Okay, we are getting 2 rows. Now combine this with insert. Okay, 2 rows affected. So this is how we do the incremental load. So since we have a primary key here, primary key, which is customer ID, we have joined on that. In some cases, there will not be a primary key. We have to generate that unique ID by some combinations. I'll show you during the snowflake. Okay. So this is about the incremental load. SCD, we'll see tomorrow. Tomorrow, are you okay with the tomorrow session?
No.
No. Okay, then we'll continue on Monday. So Monday we will see SCD. We will complete SCD and start with Snowflake.
To understand today's class, or it will take 3 days time, Prabha. If we continue tomorrow, also we will like.
Okay, please practice this. So this
Yeah.
is really, really important. These are the topics asked in the interviews, and also the same thing you will implement in the real-time scenarios as well. SCD incremental. Okay, this is one. And data warehousing, data modeling. Okay, please download these 2 files and let me know if you have any questions. Please practice, practice. Otherwise, you won't be able to get it. It might seem simple, but as you write, you will see the complexities. Okay, you can drop off if you don't have any questions.